Then, I put you in the hands of Suddhasattwa Brahma for a final talk. Thank you very much. No, but I shouldn't mention note one other thing. This is one of the two prize-winning talks, a talk based on one of the two prize-winning essays from our essay contest this year. So we're kind of going out on a bang here. So congratulations for that.
So thank you for that, and thank you for this opportunity. But all the talks at this conference has been very, very interesting. So already the expectations are pretty high. Now he's raised it further, so this can only be an anticlimax. If you have a flight to catch, I understand fully. So also the title of the talk is the same as the title of the essay that I wrote, and Chris suggested that if I wanted to keep the same, I said yes. And then I came here and I realized that I shouldn't have used words like emergence in front of a room full of philosophers, because I think I'll pay for this, but let's see. Okay, so just one thing is, while I'm giving this talk, if anybody has any questions, please stop me. I don't mind going over some details. I would rather that the main idea gets conveyed. So if you have any questions regarding any technicalities, I would love questions even when I'm giving the talk. So this is based on a lot of work done with my collaborators, mostly my PhD supervisor, Martin Bojewald, but also many other people. This is a list of, well, I think a partial list of the papers that are important. So a common expectation, as we have heard many times during this conference as well, is that space-time turns very fuzzy. It's really exotic on the fundamental level. We don't even know what are the UV degrees of freedom. Sometimes they're very different from the usual space-time that we are familiar with. There are exceptions like asymptotic safety, which we heard about a little bit, but mostly this is a very common expectation across different approaches. And the general expectation really is that, again, that you can have something like spin network graphs, so these are just algebraic data or some non-commutative coordinates and so on in the UV. But then in the usual classical limit in the IR, you regain general relativity, which is like a theory of smooth continuum manifolds. But what is more specific, of course, is what happens precisely to space and time in the deep quantum regime. This depends on the kind of quantization techniques one uses. So maybe in string theory or something similar, space-time might really be built out of entanglement between different parts of your abstract space that you have, or whereas in other theories it might be built out of spin network graphs and so on. So the main idea that I am going to push towards today is that if we start with, we do not take for granted this expectation that quantum gravity will modify radically our understanding of space and time. Rather, we start with well-understood classical systems. We apply quantum corrections, or we apply quantization techniques from loop quantum gravity, and we end up with something that is really exotic, that has some exotic geometries. I will, of course, define what I mean by exotic and fuzzy later on. And the main idea that will come in is this new notion of deformed general covariance. So the main idea of symmetries of GR, which is this coordinate freedom, they will have to be deformed in order to accommodate for quantization techniques coming from loop quantum gravity. So the outline is going to be, we will include quantum corrections from loop quantum gravity, but using covariance as a guiding principle at each point. These will lead us automatically to some deformed notion of these underlying symmetries, as I've mentioned, in this kind of background independent quantizations. So this is an important consistency check, because we know already in gauge theories in QFTs from the standard model and so on that not always quantization respects the symmetries of the system. So the consistency check here is that I can have some quantization scheme, and it might be very nice, and it might give me even singularity resolution, which is a very nice result, but does it respect these symmetries of the space-time, or the symmetries of the system it started out with? And that's the consistency check. And we'll find that using this kind of a consistency check, we will get some non-Riemannian spacetime. So this is a very remarkable result for us, because this is not what we started to get. We were just trying to see how robust singularity resolution is and things like this. So what we really, the motivation for loop quantum gravity in this kind of systems was, can they resolve classical singularity? And then using some very simple consistency requirements, you find that not only does it do that, but it also gives rise to some very non-Riemannian space-time structure. In particular, this physical effect is called signature change. So there's a non-singular effect, so the singularity is resolved, but through signature change. And I will obviously discuss some conceptual consequences of these kind of effects in these deep quantum regimes, in these high curvature regimes. This cartoon is, I think you have seen some version of this already at this talk, that we don't really know what happens to space-time in the deep quantum regime. Okay, so of course we would like to do all of this in 3+1 dimensional gravity and show you results for the full quantum gravity system. We can't do it in any approach that I know of. So also not in loop quantum gravity. So what we do is we do the next best thing. We look at simplified toy models, and then we try to see what results that can we draw out of the simplified models, which has a hope of generalizing. But for these models, once I have this assumption of using symmetry-reduced models, we will explicitly realize this expectation of this exotic geometries and this emergence of time. Again, something I have to explain to you what I mean by that later on, under two rather general and reasonable inputs. And this is a slight justification of why we are using symmetry-reduced model. The main justification is because we can't do for it full gravity. But the other reasons are like, these are simple enough playgrounds, that's true, that I can test ideas of loop quantum gravity, but they still share some features of the full theory. So these are not absolutely mini-superspace models like quantum cosmology, because they have inhomogeneity or anisotropy, in particular for some spherical symmetric models and Gaudi cosmologies that I will be focusing on. And the main result that it does show up is that you do still have singularity resolution, thankfully through this kind of loop quantum gravity quantization. Finally, of course, these kind of models are also have very interesting physical consequences for cosmology and early universe, early universe cosmology and black hole models. And this is a crucial point, because quantum cosmology, as done in the mini-superspace model, is very nice, but only if you can add perturbations to it. Otherwise, it's not realistic at all. But if there is some sort of obstruction of adding inhomogeneities to your quantum cosmological model, then it's not very useful physically. But if you instead if you can do that, you can use some sort of other cosmologies, like Gaudi cosmologies, which might not be realistic, but they have inhomogeneities, or use FRW plus inhomogeneities, and you can quantize that. That's more interesting, because that's what you really observe, what you need to for observing CMB data, for example.
So sorry, what were the two reasonable inputs?
We'll go there. So just there will be two reasonable inputs. So, okay, so good question. Input one is this canonical quantization technique, in particular of loop quantum gravity, that I'll be talking about, must respect a well-defined notion of covariance. So in this part, I will not focus on loop quantization technique in general, but this is just the requirement that I will expect my theory to have, that you have this, it respects this notion of symmetry, as I said. So brief background would be, why is covariance so big in this formulation? Is because in the Lagrangian picture, in the usual, not usual, in the other picture, when you have this kind of action principle, it's not that crucial to go back and check covariance, because things are manifestly covariant at each point. But in this canonical picture, they're not manifestly covariant. You do choose some spatial hypersurfaces, and you foliate it using some time function. Of course, this time function is arbitrary. Your time might not match mine, but there are gauge transformations which we can use to relate to each other's foliations. And this part is obviously, this is completely classical GR. And of course, covariance is not lost, it's just not manifest. And the fact that it's not lost can be seen by looking at the Hamiltonian of the system. So the Hamiltonian is a fully constrained system. The Hamiltonian is a linear combination of constraints. So it's zero. So on the constrained surface, the Hamiltonian is zero, which tells you there's no preferred time or some absolute time that you have for GR. And the point is, this Hamiltonian constraint generates time reparametrization, so that generates a symmetry. The diffeomorphism constraint, which means here the spatial diffeomorphism constraint, they give you symmetries on the spatial hypersurface, diffeomorphism on the spatial hypersurface. And mostly because I'll be working in this first-class formalism for loop quantum gravity, you also have this Gauss constraint, which gives you like a rotation of these local triad fields that you have. And once these constraints are satisfied, the theory that you have is covariant. That's the whole idea of classical GR. So one of the requirements for this is that these constraints satisfy what Dirac called a first-class system. So they must satisfy this Dirac hypersurface deformation algebra. which is given in here. So basically, the requirement is that of a first-class system is that the generators of these symmetries must close into the same generators. And in particular, they satisfy this algebra for classical GR. The best, or I guess the easiest way to think about this, or what I find to be easiest, is this is sort of the generalization of the local Poincare algebra. So if you have a flat space-time, your symmetries are given by Poincare algebra, whereas for general GR, your symmetries are given by this hypersurface deformation algebra. This is, of course, an infinite dimensional algebra because, well, and the point is, this is not really an algebra. This is, mathematically speaking, an algebroid, because in this relation, you have the inverse of the spatial metric appearing. So for an algebra on the right-hand side, we have some structure constants, whereas in this case, you have a phase space function appearing. So that makes things slightly more complicated, because we understand fairly well how to represent Lie algebras, but we do not know that much about how to represent Lie algebroids, which this one forms. And the idea here is, again, very simple. If you take, this picture shows that if you take two normal deformations, but in reverse orders, you end up on the same hypersurface, which are related by a spatial diffeomorphism. That's what this picture is showing you. And similarly for the other relations. The n is like this, the usual laps, and the n1, the w's are for the shift vectors and so on. It's not very important for our purposes, the exact structure. Why is this algebra so important is because it has been shown that the Hamiltonian and diffeomorphism constraint, as you derive them from GR, satisfy this algebra. But it goes beyond that because invariance under this algebra actually implies general covariance. So how it does that is like in this canonical theories, if you have some phase space function and you take its gauge, you take its Poisson bracket with these constraints, you end up having the Lie derivative of this function along this space-time vector plus some terms which are given by constraints. So on the constraint surface, this is exactly equal to coordinate freedom, which is given by this Lie derivative of the function along your space-time vector. So why does this go? So the first result is that if you start with this algebra and you say I will restrict myself, I will choose these generators that I have to only second-order derivatives of the metric, then you regain Einstein's equations uniquely up to the cosmological constant. So that's a very strong result because you just start with this algebra, you write them down in terms of metric and extrinsic curvature, but only restrict yourself to second-order derivatives, and you can get back Einstein-Hilbert action up to the cosmological constant uniquely. This was done by Kukash, Hoffman, and Teitelbaum in the 70s. And this shows that you have a slicing independence because it doesn't matter how you slice, how you choose your hypersurfaces. Yes?
Isn't there the restriction about the space-like embedding as well?
Yeah, so that's right. So all of this is for Cauchy, like for hypersurfaces where you can globally hyperbolic spacetimes. Exactly. And then there's this but it's also important to realize that this is an off-shell property of the hypersurface deformation algebra. And the point is, why it's important to remember this is an off-shell property is because invariance under this algebra implies general covariance. GR happens to be a general covariant theory, but not the only one. For example, you can have a theory that you have R plus R squared. That's also general covariant because you contract your indices the correct way. So starting from this algebra, you can actually regain those actions as well. So why do you uniquely get GR is because you restrict yourself to second-order derivatives. If you go to higher-order derivatives, you get higher curvature actions. So invariance under this algebra is beyond GR. So solutions of the constraints, if they're derived from GR, of course, gives you Einstein solutions. But if those constraints are derived from some higher curvature action, then no, then the algebra is still the same. And this has been also shown by several people whose references I should have here, but I don't, sorry. So this algebra is more powerful than GR in this particular sense about the symmetries of spacetime. Okay, so now let's come to quantum modifications. What do I mean by that? What do I mean by that? So of course you can have some modifications to your action here, and as an effective theory, you can think that low energy effective actions are always going to be R plus R squared and R mu nu squared and things like this. But also you can change the measure. And what I mean by changing the measure is that you can change this definition of covariance in a way that you do not have an invariant measure perhaps anymore. at this point, this is just a speculation. I haven't told you why one should do that or one should think about these things. But the point is, in this action, there are two places where quantum corrections can come in, really. And usually we are way too focused on like how the Lagrangian changes, but there can be also changes to the measure. And what I will hope to show you is that canonical quantization in this particular formulation will tell you that you have to change this measure because you have a different notion of covariance. And this is kind of a little expected from this uniqueness theorem that Hoffman, Kukash, and Teitelbaum showed us, because if you start with the same algebra, you're guaranteed GR up to second-order derivatives. So if we are restricting ourselves to second-order derivatives and we want some other action which comes as an effective action for a quantum gravity theory, then if it isn't GR, then you have to break some of the assumptions of this uniqueness theorem. And one assumption you can break is that you don't start with this algebra, but you start with something that is similar but deformed. Okay, so I have said a lot about we should focus on this as a consistency condition, that you should have a general covariant quantization. So what do I mean by that? What I mean by that is you have the classical constraints and then you replace them with some generators in your quantum theory. So you have some quantum operators which must still have closed brackets. Now, how these brackets are evaluated depends on the particular theory you have, how far down the line you have developed the theory. So they might be really commutators on your Hilbert space, or they might be some modified Poisson brackets as an effective theory. But these brackets of these quantum operators that you have should, or this quantum corrected classical operators that you have, should still give you a closed algebra. So on the right-hand side, you must still end up with some constraints or quantum corrected constraints. You cannot end up with some term that doesn't look like a constraint, because that would be an anomaly. And the second requirement is that whatever new brackets that you get, so now let's say you have a different algebra of this of these operators, but they must have a well-defined classical limit so that you regain Dirac's hypersurface deformation algebra. Because you know classically your space-time is Riemannian, and this algebra is telling you that these notions of covariance in Riemannian geometry is true. So you must regain this classical limit of whatever new constraint brackets that you have now. This is the two requirements that I will demand of any quantization technique, canonical quantization technique. So this is only for people who are familiar with loop quantum gravity literature, is that this second condition is slightly more, it's a further requirement, because you don't just require that brackets are closed, but that also they have a well-defined classical limit. And this is slightly goes beyond what have already been done in the LQG literature. Okay, so what's the input 2? So input 1 is, again, that you must have a covariant quantization technique. Input 2 is that singularity resolution in LQG happens due to non-perturbative corrections. Again, the input is not going to be to justify singularity resolution in loop quantum gravity. I'm just going to tell you how it happens, and I'm going to extract what is the main effect coming out of this singularity resolution. That's the input. I'm not here to justify LQG singularity resolution at all. So the way this happens is, on the kinematical Hilbert space of loop quantum gravity, we have not well-defined operators for the connections themselves, but only for holonomy operators, which are parallel transports of these connections. And then this curvature operator, so local curvature operator in GR is now regularized using these holonomies, which introduces some non-local corrections in loop quantum gravity. And this has also come up, and this has been discussed to some extent. Generally speaking, the Wheeler-DeWitt theory has been shown to have some pathologies as GR, so they do not usually solve the singularity problem of GR, but as also has been shown that they do in some cases. But in general, they don't, whereas you also have this Stone-von Neumann uniqueness theorem, again, for a finite dimensional phase space, which I should also mention is not just on R+, as has been already pointed out, but at least for this, so this theorem sort of indicates that the only quantization you can have for like a finite dimensional system like a quantum cosmological model must be unique to this Wheeler-DeWitt quantization. So how can you have singularity resolution? And the point is, the way LQC violates this is by violating this weakly continuous assumption. So because these holonomy operators are not weakly continuous, so you don't have to have a representation that is unique to the usual Schrodinger quantization. And this is how they bypass this uniqueness theorem. And then I don't actually require, again, these are things which one has to justify if one wants to justify singularity resolution. I don't plan to do that. I only plan to extract a very simple effect coming out, well, not very simple, but one effect coming out of all these mathematical calculations, which is this inclusion of holonomy corrections coming from loop quantum gravity. So doing all this essentially means that now you replace your curvature operators, which was written in terms of connections, in terms of holonomies, and now you can write them in terms of these holonomy corrections coming from loop quantum gravity. Of course, again, all of this for symmetry-reduced models. Okay, so again, the singularity resolution, the crucial feature is this, what is known as also polymerization of this connection component. So usually what happens is if you have a connection, you replace it by this sine function divided by delta. Delta is some parameter which is related to the Planck length and the Mirzi parameter of the theory and so on. So of course, as you see, when delta goes to 0, you get back k. Now, the important point here is that this is not a choice. This is not something that one comes up with. This is not an ad hoc choice one makes just to regularize. But this is a derivation in the theory. You find that...
What's k? Sorry.
K is just any extrinsic curvature component, let's say. So it's just generic. Like in loop quantum cosmology, I would call this C. But it's just standing for any.
But it's loop quantum cosmology in the context of here? Or?
I will talk about spherical symmetry, but you can think of right now. You can think of loop quantum cosmology. That's perfectly fine.
Not loop quantum gravity. That's right.
No, it's all symmetry reduced. Everything is symmetry reduced. So usually this comes out to the sign, and this is again the result of a very rigorous derivation. And this has some inputs like which spin representation you choose and so on. Again, not important. In fact, what I will work with is I will replace this function by this k with this extrinsic curvature component by some arbitrary function, which will allow for quantization ambiguities like what spin representation you are choosing and so on. The only restriction is that, as you see, this function is replaced by, in this case, cyclic function, but oscillating function. But I just require the f to be bounded. That's my requirement. And again, this is not an external requirement. This is not input 2 prime secretly in here, because this is the result of the regularization in loop quantum gravity. You replace these extrinsic curvature components in the symmetric models by some bounded function. Now, what this bounded function is depends on different choices in the theory. I don't want to show you that my results hold for each choice, so I just keep it arbitrary and put an f there. And this is very robust within symmetry-reduced models. So within symmetry-reduced models in loop quantum cosmology, there's a whole host of literature, I think at least 100 papers on this, which shows that there's definitely singularity resolution. Also for black hole models recently, there's a lot of papers coming out for Schwarzschild, for CGHS black holes, and also for Gaudi cosmologies and so on, very recently for so other types of cosmologies than Bianchi models and FRW. So this is very robust and has been demonstrated across a lot of different symmetry-reduced models in loop quantum gravity. So, okay, what's the big picture? The 2 inputs are done. Let me just recap very quickly. So I started with a classical set of constraints which form a closed system, but now there are phase space functions on the right-hand side and not just structure constants. I include some quantum corrections. In particular, I will include these holonomy corrections as I just defined them in these constraints. And so I'll have some quantum corrected constraints that I'll work with. And I will calculate the algebra of these quantum corrected constraints. Now you see, I don't just write f here and put hats on it, because now I probably should put like CQ here for quantum corrected, or at least these hats are supposed to remind you now. These constraints are not exactly the same ones as the classical ones with just hats on it with factor ordering ambiguities, but they're rather different because they have already been regularized to include these non-perturbative corrections. So this function on the right-hand side is going to be, not going to, but can be different from this classical structure function. And even more, anomaly freedom is a requirement that you get this. I mean, I'm not sure a priori that I will get that. I can get plus some term which is not proportional to any constraint at all. So in which case I have an anomaly in the theory, and that's really bad, because if you have an anomaly in this kind of theory, you're not breaking some internal symmetry, and that's okay, but rather you're breaking gauge. So in this case, that would mean that why is it important to have the closed algebra here is that the number of spurious degrees of freedom that you have in your theory must be, the number of real degrees of freedom must be the same, unless if you start having anomalies, the the generators will eliminate lesser number of spurious degrees of freedom, and your degrees of freedom counting will have a mismatch. And again, for whatever new algebra that I get, I will take, it must have a well-defined classical limit so that I can get back my hypersurface deformation algebra in the classical limit. Yes?
So I'm interested, so whenever I've seen people, probably massively out of date, trying to quantize the Hamiltonian constraints, they have to use different techniques, like master constraint techniques.
Right.
So what procedure would you use to quantize the Hamiltonian constraint?
Yeah, so I don't have to worry so much about that because I'm not working full loop on gravity. So that master constraint and things like that will come up in the full theory. In the symmetry-reduced model, you just introduce this kind of polymerizations, and you find that a Hamiltonian constraint is somewhat different. Like you have replaced your C's with sine C for loop cosmology, and then you try to quantize it.
Standard quantization techniques.
Right. You then use standard loop gravity quantization techniques. Yeah. Okay, so the two inputs are there. Now let me try to develop my output, which is that you have signature change and this emergence of time. The best way to do it, I think, is by looking at a particular example, and I will look at spherical symmetry just to emphasize this point that this theory does have inhomogeneities and so on. So this is not just mini-superspace, this is midisuperspace. So you just write things in this kind of unfamiliar coordinates, of course, in loop quantum gravity. K phi and kx are components of your extrinsic curvature, which are conjugate to your densitized triads. And so these are the usual coordinates one uses in loop quantum gravity. And then you can write down the spatial metric in terms of these coordinates. So yeah, it's just a fancy way of writing things that are already known to us. And then the implementation of this local holonomy corrections, and maybe this is the point you had in mind, is like we can only include corrections which are local in the theory so far. That's why we can't do it for the full theory. And this, I will come back to this criticism at the end. So we can write down the constraints for this theory. We can write down what is H and what is D. And then what we will do is wherever I see k phi, I will replace it with this function of k phi, which I don't know, I keep it arbitrary. It's some function of k phi. And then I will calculate the brackets between H and H. So I will only show you the H and H bracket because the other brackets remain the same. It's the same as in classical GR. But the H and H bracket now has a deformation function in here, which I denote by beta. So beta is equal to 1 classically, but now this function is actually the second order derivative of this modification function that I had introduced here. And the point of signature change, very simply put, is that this function, this deformation function, has to be negative at the maxima of this function. The classical singularity is exactly where this function reaches its maxima. You have singularity resolution precisely because due to your regularization techniques, you don't have k phi, but you have a bounded function of k phi there. So now, where the classical singularity was, this function must have a negative sign. So this bracket has a negative sign on the right-hand side. And what it means is that this kind of, once beta changes sign, this brackets have the same sign as is for Euclidean gravity. So in this precise sense, I mean signature change, that now my hypersurface deformation brackets, you can calculate them for Lorentzian gravity, and you can get classical Lorentzian gravity and classical Euclidean gravity, and you find that the change is that the H with H bracket has a different sign in both cases. And in this particular case, when beta is 1 in the classical regime, you have a positive sign here, and then it goes to some negative value. Of course, it's not negative of some deformation here. It's not exactly Euclidean. It's some fuzzy Euclidean. So this is what I mean also by fuzzy, because it's not exactly Euclidean, but it's some quantum regime, but it has the same sign, the brackets have the same sign as for Euclidean gravity. So in this sense, we have signature change. But this is a consistent deformation, like, yeah.
You're going to tell us that, is there an intuitive way to see that from the bracket, or if not, that's fine.
There is, and I will come to that at the end. Yeah. So the point is, of course, you can deform gravity in many different ways or include different corrections, but this is a consistent deformation in the sense that I have not broken any gauge condition. I still have brackets which close, I still have constraints which close into each other. So I haven't broken any of my symmetries. I don't have anomalies. That's why I call it consistent. But also there are problems, like you don't have any effective line element anymore. So that's because the DXAs in this effective line element do not transform on the same deformed gauge transformations as QAB. So the point here being made is that one might naively think that you can just write this new guy as Q tilde AB, and then everything is fine, and like in classical GR, but that's not true because the transformation properties are different. They don't obey the same transformation properties. Nevertheless, one might think that you can start with different field redefinitions, that you can do some canonical transformations of your original fields, of the original fields that one works with, and in that case, you can maybe absorb this factor. And I don't have the time today to actually explain to you why that doesn't work, but I will have a slide where I'll show you why that doesn't work. So this is a difficult thing to prove in general, because no matter how many canonical transformations I show you, and I show you that it doesn't work, you can always say that, I was not clever enough, which is probably true. But I'll try to show it from a different mathematical viewpoint why no such field redefinition will ever take away this factor completely. And as I've already mentioned, that signature change, however, does resolve classical singularity, because you see, the classical singularity resolution happens in the terms of this function k phi being replaced by a bounded function. So in terms of cosmology now, if you think of the Friedmann equation, you have h squared, which h being one of these extrinsic curvature components, is equal to something, and then you can write the effective equation as sine of h squared. So that's why h never diverges and so on. So that way, the signature change still resolves classical singularity. But this is a new model of quantum space-time, and if you cannot write an effective line element, then you do not have a Riemannian structure available to you anymore. So you have signature change, but it comes at a very heavy price, that you have to abandon your classical notions of Riemannian geometry in the deep quantum regime. Of course, you regain all of this once you come to the semi-classical, the classical regime. And then, of course, if you cannot write down an effective line element, you cannot write down an action, so how do you do any calculations for observables? But the point is the Hamiltonian formulation is absolutely well defined. That doesn't go away. You can still have observables which will be calculated, the dynamics of which will be calculated by the brackets generated by these constraints. And this is the result, which I'll just tell you, is that I already referred to this hypersurface deformation algebra as Lie algebroid. And the reason why I invoke this here is to show you that just like you can have algebra transformations to show that different algebras are equivalent, you have algebroid transformations to show that which algebroids are equivalent. And the point is, you can actually absorb the magnitude of beta using different algebroid transformations, but the sign of beta cannot be removed by any algebroid morphism. This is something which you can prove rigorously that we did in this paper. Of course, I'm stating here this is a result, and I'm not showing you the proof. But this is an interesting point, because a priori these betas are just functions on space-times, on phase space. So you'd imagine that there is like infinite number of inequivalent algebroids that you have here. It turns out no, there are only two. One which can be locally reduced to Lorentz geometries, and one which can be locally reduced to Euclidean geometries. But there is no one space-time geometry which you can have which is a global, which globally covers the full transformations, the full deformations, and that's the point. So again, just to clarify, absorbing away the magnitude of this deformation does not obviously mean that there is nothing that you see. In the equations of motion, these deformations will come up again if you even absorb them away in the brackets. But the point is, the brackets only tell you about the space-time structure. Equations of motion tells you about how matter and other things, or even gravity itself, move. So these are two different things. You might have a space-time structure that is still Riemannian but modified, through quantum corrections, and then your equations of motions will have these modifications. But at least you have Riemannian geometries. In this case, so that would be a case where beta, let's say, is positive. So you can remove this beta. You have a model of Riemannian modified geometry. And of course, you will see these corrections in your equations of motion. But at least you can have the same structure of geometry or space-time that you have classically. But in this case, when you have the beta changing sign, you don't even have that. Locally, you can have that, but not globally. You don't have globally defined space-time structure that resembles Riemannian geometry.
So you don't have that picture that usually people put in the Hartle-Hartman that you cap off with an Euclidean geometry. Here you wouldn't have geometry after this change of sign.
No, we would have some geometry. I don't know what. So all I can prove is that it's not Riemannian. I don't know what kind of geometry it is. I will come back to that question. So how seriously should we? So this is a very strong statement, of course, that you have singularity resolution, but through something that is rather, well, difficult to understand because you give up on very well-established notions. So how seriously should we take these results? And this was already shown in cosmological models by other people dating back to 2012. Actually, that's where it was first, I think, found. But these were cosmological models with perturbations. So this is an important distinction because if you make your model very simple, like if you just have a quantum cosmological model, then your diffeomorphism constraint that I defined here on the right-hand side is uniquely zero because you don't have any special diffeomorphisms left. And in that case, you will not see any such effect because, well, your right-hand side is zero. You don't know what's happening. So there is this danger of oversimplifying, of course. And so the point is, if you have a cosmological model with perturbations, the perturbations are very small. They don't cause the effect. They are just important for you to realize that such a thing happens. So that's why the results of symmetry-reduced models have to be taken with a grain of salt. And then we generalized it to other black hole models. Of course, I've shown you the result for spherical symmetry, so which would be a Schwarzschild, but also this 1 + 1 dimensional CGHS, and also for other models such as Gaudi models. And in fact, we managed to generalize it for a general midisuperspace model. So we have a 1 + 1 dimensional, so we have one-dimensional inhomogeneity. So of course, again, this is not generalized in the sense of 3 + 1. We have one-dimensional inhomogeneity. And for any such model, so this kind of models include Schwarzschild and the Gaudi models and CGHS black holes and two-dimensional Wiltonic gravity and so on. And for any such model, we don't even need to specify how the triad terms in the Hamiltonian constraint appear. So you can actually allow for things like torsion and so on. But as far as you still include holonomic modifications like the one I talked about, this necessarily leads to singularity resolution and signature change. So one idea was maybe perturbative correction. So this is, of course, just focusing on this particular kind of non-perturbative correction from loop quantum gravity, holonomic corrections. So maybe perturbative corrections can cancel this effect, and then you wouldn't see it. And the short answer is no, it can't, because, well, we found this in this paper that this quantum back reaction of this moment, so you don't just work with expectation values, but also you think of now fluctuations and covariances and higher moments of your state. So can those things cancel this kind of effects? And we found that no, they can't. And of course, in any such perturbative treatment, one might argue that, well, your conclusions cannot be true for deep quantum regime because the perturbative treatment probably breaks down there. Actually, you can have some conclusions about even the deep quantum regime, about the algebra. And this is something I'm happy to talk about more later on if anyone has questions. And this is also understandable from this higher curvature thing that I already told you about. So people have shown that for higher curvature actions, as I've already mentioned, you have the same algebra as that for GR. You have the same hypersurface deformation algebra. And in the canonical theory, this kind of quantum back reactions, this kind of higher moment terms are supposed to capture higher curvature corrections. So if higher curvature corrections do not change your algebra, so shouldn't higher moment terms. So this is just this is just consistent. This is maybe an independent way of seeing why this doesn't take away these corrections. How much time do I have?
10, 15 minutes.
Okay, so we also did this sort of robustness check with other models in loop quantum gravity where mathematics is very different. They first abelianized this Hamiltonian constraint in the sort of master constraint way, and when they quantize it, they find that everything is well defined. You have covariant quantizations, but again in their models, if you then go and check what is the classical limit, you find you have exactly similar sort of deformations coming up. I don't want to spend too much time on it, but on every model that we have, there's an actually independent analysis by some other group, and it turns out that we match on this kind of result. Okay, so how do I interpret these results? And I break this up into some things which I'm very confident about, some things not so much, and some things I'm definitely very speculative. And let's see what you all have to say about these things. So the confident results are that we have some sort of deformed covariance. Why do I call it deformed? It's just because I know the hypersurface deformation algebra tells me I have covariance. If there is some deformation function appearing there, that's what I call deformed covariance. That's just I guess, the name we choose for it. The physical effect is signature change. And you see this sort of going from this fuzzy 4-dimensional to 3 plus 1 dimensional Lorentzian space-time signature. Of course, you don't do this in 3 plus 1 and 4D, but the point is you go from some fuzzy Euclidean regime to Lorentzian regime. Why fuzzy? Because this is not exactly Euclidean geometry, but something which has the same signature as Euclidean geometry. But remember that in this deformation, even before beta changes signature, there is a phase where beta has the same sign as for Riemannian geometry, or pseudo-Riemannian geometry, but it's not exactly Riemannian, of course, because now you have some deformation function sitting in there. So in that precise sense, this deep quantum regime is fuzzy Euclidean. So what came before this phase? Like, can there be a bounds picture, which is the most common picture in loop-quantum cosmology? So this doesn't answer that question, actually, because I just showed you that this signature change happens, but in the mini-superspace case, we know that there is this bounds picture, which is very well understood, and maybe there is a bounds picture here as well. That would just mean that you have a contracting branch and an expanding branch, but in between, it's not a smooth bounce like people usually think it is, but rather in between, there is a region of this deep quantum fuzziness, which has a wrong signature as compared to our usual, to our universe. So maybe what replaces, so I know this is not Riemannian and globally, so what replaces this geometry? I don't know, maybe non-commutative geometry, maybe non-associative, fractal. I'm just throwing words here, I can be as speculative as I want. But maybe, so then look on gravity's techniques are telling you that maybe this is what you should really look towards, like they're capturing some features there. I of course don't, at least I don't think that this is the full physical picture, that you really have signature change, and this is exactly what happens. Maybe all this is telling you is that at that deep quantum regimes, you have something very exotic going on, and this is just giving you an effective picture. You effectively have signature change, but maybe the notion of signatures and things go away at this level. I don't know. So this is to answer Nick's question earlier on, like, is there some intuitive understanding? It's like, if I start from the hypersurface deformation algebra and I restrict myself to flat patches, then I can regain the Poincare algebra. I can derive the Poincare algebra starting from the classical hypersurface deformation algebra. On the other hand, now if I include this kind of beta corrections, and I say that the beta doesn't change sign, so I'm in this Lorentzian patch, then I start with that deformed algebra, and I try to derive its flat limit. What I get is this kappa Poincare non-commutative spacetime. So it's not Poincare anymore, but it's still like Poincare, but it's non-commutative. So this is why we think it might be non-commutative. I wasn't just completely guessing these things. But also, now if I do the other thing, that I go to the signature change regime, so now I'm a beta changes sign, and I try to derive what is the flat limit, I again get like a deformed Euclidean Poincare. So, and of course, if I know then that if I take the other sign, that is already well known that it would be Euclidean. So some of these results are published and some of them are forthcoming. Okay, so what are the less, so I didn't want to say these are the moderately confident, so I just said that these are convergences with other approaches. So already I've talked a little bit about non-commutative geometry. There's also other reasons independent of this analysis why people think there might be some relation between loop quantum gravity and non-commutative geometry arising from lower dimensions. So I've already said all I had to say about that. But there's also some similarities with other approaches like causal dynamical triangulations, because in this kind of approach you have some geometric phases in the UV, which some phases in the UV which are non-geometric, and even Daniele mentioned some phases like that might exist in the GFT picture. So the point is, if I think of deformations of the hypersurface deformation algebra as equivalent to gravitational phase transition, so beta changing sign, if I think of that as a gravitational phase transition, then you can formalize this relationship a little bit more, and you can show that maybe even this exotic fuzzy Euclidean regime might be closer to this crumpled Euclidean gravity regime in CDT, and then you get back your Lorentzian usual GR in this low curvature regime, like you do here once you are in this beta is positive regime. So some work has been done by Jakub Milcharek in this direction. Also, there are many implications for black hole complementarity principle. I think none of this is at all concrete, so that's why I said I'm moderately, these are sort of hopes that I can make connections between them rather than there are already established connections. So the point is, inside the core of the black hole now, you would have some fuzzy Euclidean regime again. So you really would have some sort of indeterminism creeping in, because now your equations are turning from hyperbolic to elliptic in this region. So just giving some initial condition outside the horizon will not let you pass through this region inside the black hole. So even if there is black hole fireworks or bounce in the black hole picture, which is not what I'm advocating at all, but even if there's something like that, it has to go through this fuzzy Euclidean regime where you need additional conditions. And this slightly reminds us of the stretched horizons which come up in black hole complementary principles. But this is just heuristic. There's the mathematics that we have done to prove that anything of this is happening actually. The Hartle-Hawking thing came up already. This is reminiscent of Hartle-Hawking, but of course in the Hartle-Hawking case you have this initial instanton which you do a weak rotation and so on. So I don't want to say too much about this because this is probably the one thing that I am currently working on, so I will be happy to talk about this later, but it's just reminiscent in the sense of this signature change, very general sense. But finally, there's also things like which you can calculate of the spectral dimensions. So you can calculate the spectral dimension of a space-time, and if you calculate it for classical geometries, you get the usual 4 dimensions that we know there is. But then you can do these calculations in the UV for different theories, and Daniel A. and collaborators did this for loop quantum gravity, where they looked at this like as combinatorial complexes. And the thing that they found is like you go to some lower dimensions in the UV, the spectral dimension flows to some lower dimensions in the UV. And our initial results also for this kind of canonical analysis, including this kind of deformations, show there is actually a remarkable similarity between the way this flow is taking place in our case from this low dimensions to 4 in the IR as compared to Daniel A.'s work. So these are, I mean, I know they are both from RealQG, so you might assume that they should be similar, but they're based on very different mathematical techniques and even constructs. So a priori, I wouldn't have expected them to. I mean, of course, I expected to go to 4 if my result has to be meaningful. But in the UV, it could have flown to other things, and even not just that the value it flows to, but the way it flows to it is also very similar. So as I already mentioned, none of this has been made rigorous. None of these papers are published yet. But this is exciting for me because we severely lack guidance in quantum gravity, and looking for convergence seems to be a good idea. If there are ideas which come out of different mathematical constructs, out of different theories, but they converge on their overall picture, those ideas I think are worth pursuing much more. So that's exciting for me. So now completely speculative claim. So this is the fun part. I have 5 minutes, is it? 2 minutes?
Yeah, 2 or 3.
Okay. So Bergman said this back in 1949 that there's no particular reason why theory of relativity must appear in the form of Riemannian geometry. And if indeed that you believe in our model, which is for symmetry-reduced case and so on, but if you believe in that, then this seems to force us to abandon notions of Riemannian geometry in the deep UV. And maybe we don't know what replaces it. We don't know even, as Henrique said, that even if there is some well-defined geometrical objects, but at least we know it is not Riemannian. And then Dirac said that it would be permissible to look upon Hamiltonian form as the fundamental one, and there would then be no fundamental 4-dimensional symmetry in the theory. And if you take our work seriously, then we do know that there is a regime when you cannot define an invariant measure, you cannot define an action, but your Hamiltonian formulation is perfectly fine. So so this would suggest that indeed this is more fundamental in some sense. Now, there can be a question that can I not come up with some theory where the Hamiltonian formulation fails and the Lagrangian one survives? Sure, I'm sure like you can do that mathematically. But the claim is loop quantum gravity is a theory of physics, and if you believe that, then this seems to suggest that Hamiltonian is more fundamental. So what are limitations, possible generalizations? I'll go over them very fast. One is that these have been realized in symmetry-reduced models. That's absolutely true. I have no counter to that except to say that, well, so has been singularity resolution. So if you take these results seriously, you should take these ones seriously as well. If you say singularity resolution is for 2 restricted models, then sure, these are for 2 restricted as well. And then there is this technical objection that these are for at the level of effective theory. So you work with expectation values of operators. Well, this was true for some time, but this is not true anymore. We have results for operators in Hilbert spaces, at least for spherical symmetry, not for all the models that I've discussed. And even for symmetry-reduced models, actually, we have some no-go results, which show that it's not easy to do this kind of analysis for theories with local degrees of freedom, like spherical symmetry coupled to matter. And so what happens there? Because that ends up having some anomalies, and we don't know what is a good choice to explain or to wish away these anomalies, or how not to have them in the theory. Well, the answer to that is this is a result. This is not something that this is not an artifact of our method or anything. This is the same result comes up even if you try to do quantization of spherical symmetry with matter in other formulations of loop quantum gravity, specifically by this LSU group and by Jorge Polin and others. So they find that there are similar obstructions. So this is a result. Yeah, it shows that this kind of modifications are tough to implement. But the other thing is, if you look at my inputs, the real input was that you replace this extrinsic curvature component by some bounded function. So that's really not that can go beyond LQG easily. You can find some other quantum gravity theory which gives you some sort of effective correction that looks like this. So this is not very tied down to LQG, except for this, that the function is a bounded function. That's the only requirement that LQG supplies. So this can be applied to maybe other models, I don't know. And the other thing is that this results are more about the symmetry algebra. This is about the algebra of the system, the quantum algebra, or at least the semi-classical algebra, and not about. This is a largely state independence claim. So I don't refer to spin network states anywhere for my proofs. So that's a good thing, because you can choose some other basis on your kinematical Hilbert space, and then I don't think these results would be altered. Okay, I summarize here. The take-home message is modifying gravity is really hard. I think you all know this by the end of this week. But actually, this is not my word. This is Arkani Hamid's, and he says that you have to understand gravity and not modify it. I think that's too flowery, but the first part is definitely true. It's very hard. And it's very hard in this precise sense that Daniel, in his talk, already told us that, theory of microscopic space-time is what a theory of quantum gravity is. I write space, time. I don't know if there is space-time there. I don't know what kind of space and time means. What are these concepts in the UV? So Daniel does this very difficult job of starting with some theory that has completely exotic building blocks in the UV, and then he tries to regain our known things like GR and cosmology in some limits. And he successfully showed us how to do that for some cosmologies. We are trying to do this the other way around. It's trying to say that we know some symmetry-reduced model, and I'm trying to quantize it using some certain techniques. Do I get some exotic UV degrees of freedom? And that seems to be the result that, at least for loop quantum gravity, where this kind of deformations are pointing towards exotic geometries, they're pointing towards something else. The relation with non-commutative geometry is actually a little bit more developed than I told you about. That's something that we are working on, and actually that's why Eleanor's talk was very nice, because we find also that you can perhaps have similar sort of deformations coming from constant theta non-commutativity. So the other big message is the singularity resolution is not cheap. So it seems very cheap though, like you can have singularity resolution in many different mini-superspace models, different quantization techniques, and you still don't have the Big Bang. Well, that's maybe because you are in toy models. It's one thing to have singularity resolution in quantum cosmology, and then it's another thing to say that you can embed this quantum cosmological model in a larger quantum gravity model. That's what we are really trying to do here. Like, you start with some simple model, homogeneous isotropic, you have singularity resolution. Now you say, if I add in homogeneities, is this result still true? And what are the consistency conditions? So if you try to, of course the thing then would be like to push beyond this kind of midisuperspace and go towards like full 3+1, and are then any of these results trustworthy? So singularity resolution is a great result, it's very exciting, but it's not easy. There are several technical issues which come up, and perhaps they are more interesting conceptually. I'm bound to say this, I'm working on this. And so the last thing is, I think Richard didn't quite explicitly say this, but in his talk, the point, why is string theory moving away from different ideas after like maybe 5 years or so on, the new idea comes up, is because it goes back and has this consistency relation. So it's true that you don't have empirical evidence to support your theory or your claim or predictions sometimes in quantum gravity, but you do have mathematical consistency conditions. In this particular case, I talked of covariance, and this is an important thing because even mathematical consistency conditions can bring about radical changes in your theory. And that's something that one should be seriously thinking about, because it's not enough to say, well, we don't have experiments, so we don't know if this is right or wrong. No, maybe there are other ways to also verify it. And I end there. Thank you.
I had a question about the first input
Mhm.
invariance requirement. So I was confused by one remark you made near the end of that section, which was that your Hexagon's definition of algebra is stronger than GR?
Sorry?
Is stronger than GR?
This restriction?
Yeah.
No. This is just saying that in GR we know that the constraints form a closed algebra.
Right. Oh, sorry, it wasn't this part. It was before this, I think. Yeah, it was on.
Oh, this is just saying this is stronger than what sometimes people assume in loop quantum gravity.
Oh, I see.
So it's just saying that you have a closed system of constraints. Whatever the algebra is calculated on, maybe on some kinematical Hilbert space, maybe on something else, but they must close into each other. That's the main condition. The stronger part here is like they must also have a classical limit, but that's only more or less addressed to some things that people do in loop quantum gravity.
Great.
That's really fascinating. So, like, maybe kind of quite naive level, one of the ways that I try and get a geometric understanding of the hypersurface deformation algebra, slightly obviously, is thinking about the deformation of embedded hypersurfaces. And this is one of the real beauties of the algebraic regression hyperform derivation is they start with this geometric idea about how would we construct an algebra of constraints to represent these deformations.
Exactly.
And so obviously the idea is that we're deforming the deformations. And so even for a simple example of how we can think geometrically about the what it is that the deformed hypersurface deformation algebra, or an instance of it, would be representing in this kind of geometrical picture. That would be very helpful.
Right.
To conceptualize what's going on.
My short answer is we don't know. After including this kind of corrections, we don't know if that geometric picture survives. We know it doesn't the way it is, but we don't know what replaces it either. So my short answer is I don't know, but maybe let's say if this program of connecting this to non-commutative geometry works out, then we can try to derive a geometric picture where the manifolds will not be so smooth and so on, but at least you have a picture.
And then potentially you might be able to do things the other way around, start with the geometric picture and derive your
Absolutely.
form version of the algebra, and
Absolutely.
that would be a really beautiful way.
Absolutely. So the point is, so this is really a very small step in that sense that you just show that this nice Riemannian picture is not there anymore. You don't show what replaces it, you don't know what replaces it and so on. But once we can, if we can have this kind of geometric picture again, that you have some sort of hypersurfaces, maybe non-commutative or something, which can still be embedded in this space-time, or force space, or whatever you have, then you can actually regain back what kind of effective actions that you want to from following more or less what they did. This is something that I'm looking at, but yeah, so far all I can say is that we don't know what the geometric picture is.
Enrique.
This was a very nice talk, thank you.
Thank you.
So can you just repeat the argument for why you don't have a geometry in the when beta flips sign? Why don't you have a geometry on the other side?
No, so that's actually not the argument. So the argument is like on the other side, you can always locally have some Euclidean geometry. So I just say locally because the point is, so if you look at these brackets, where is it? Wait, sorry. So there is a beta in there somewhere. Yeah, okay. So this is not obviously Riemannian, but if the beta is positive, you can write down a metric that is effectively Riemannian. So it's not the usual. Let's say you start in this spherical symmetry case. So it's not the usual Schwarzschild metric, but it's deformed Schwarzschild. You can write it in the same form. On the other side, you can do something similar. It's just that you cannot write down one metric which will capture both of them. So on this signature changing hypersurface, these things become ultra local, and this sort of light cones are collapsed, and you have causally disconnected things on the other side.
Right, but so wait, so you don't have a metric only in the transition period.
You have locally metrics at both sides, and you don't have it at the transition period, and you don't have one global metric that works everywhere. Yeah, that's what I mean by not having Riemannian geometry.
Okay.
Yeah.
The other thing that I was going to say is that, so one of your arguments for consistency, which I think I appreciate, and I think they're very nice, but as you know, they're very different when you are in the symmetry. There is a qualitative difference when you're in the symmetry.
Absolutely.
A lot of things can commute when you're perturbing about symmetry-reduced space that wouldn't commute.
Absolutely. Absolutely.
And I think it's really nice. I think it's practical, and if we can do it, if we can quantize around this symmetry-reduced space, let's try to do that. It's interesting to speculate how these arguments would translate to the full theory. Just speculation.
Yeah. So I have 2 points here. One is, you're absolutely right. These are really simplified models. It's just that once people get singularity resolution out of these models, they don't even usually go back and do this very simple check, as you said. So it's important to do this for this reason, that even for these simplified models, this kind of consistency conditions can lead to very, very different conclusions. And then, of course, you need to think about what happens for more generally for gravity. And again, the short answer is I don't know for LQG, because the fact that these models utilize for this kind of singularity resolution is that you have this local holonomy corrections. So you replace k phi with some function of k phi. But that's just because you have angular symmetry. So when you take the integration of the holonomy, you take integration k phi d phi, and k phi is just a function of the radial coordinate, right? But you can't do this, for example, with the kr or the kx. So then you have to, so the usual trick is you eliminate the kx variable classically, using the diffeomorphism constraint from your Hamiltonian constraint, and then you quantize the system with just has k phi. But of course, these kind of tricks won't work once you have full inhomogeneity. So I don't know, how will you do that? How will you approach that problem?
Ward. Are there any other hands?
Thanks for this thing.
Thank you.
Basic question. So, like in classical GR, you showed, okay, you have this independence of how you move your data, so your metric and your momentum. It doesn't matter which succession of hypersurface you take, you end up with the same result. You have some kind of foliation independence.
Right.
And I suppose that's equivalent to diffeomorphism invariance.
So the diffeomorphism invariance is like the full algebra tells you about that. Foliation independence just tells you that the algebra doesn't depend on how you foliate your hypersurfaces. So they're not the same thing.
Okay. And then in the quantum case, so this foliation independence, I have to see it the same way. You have your wave function on a leaf, and it doesn't matter how you.
In the quantum case, again, the short answer, as I said to Karim, is that I don't know the quantum, the geometry. So I understand. So
before you deform anything, right?
So if you don't deform anything, there is for me no quantum case, because for me it's loop quantum gravity where you include these corrections, and if you don't have these corrections, you don't. But for the Wheeler-DeWitt theory, it would. Let's see, what would it mean? Yeah, then I would, for the Wheeler-DeWitt theory, I would assume that your covariance works in the same way, unless you do some regularization secretly, which you don't tell me about. I would assume that. But I mean, it depends. Like strict Wheeler-DeWitt theory, in the sense of quantum cosmology, doesn't have any of these pictures, because.
Sure, I agree with that.
Right.
Just conceptually, I want to know what's going on. Forgetting about technical details. Maybe
Right.
I would have to picture it like this, that like for the Wheeler-DeWitt function.
Right.
It doesn't matter how you evolve.
Yeah, so the point is, in Wheeler-DeWitt theory, you still have the spatial metrics and things like this available everywhere. In this case, that's not the case, because you define them on holonomies, right? So there is a very important difference in these two things. Is what I understand by Wheeler-DeWitt theory would be all sorts of quantum corrections that you have are pretty local. But in this case, you have some, at the Planck length, non-locality coming in because of these holonomy corrections. So, yeah.
Seeing no more hands, I'm going to ask a question since I've been restraining myself all day. So, but maybe it's not as interesting as some of these questions. But I'm just kind of. So my question is, why do you insist on the anomaly freedom in the quantum theory? Because I mean, not all anomalies are bad, so what is actually motivating it in this case?
Right. So the anomaly. So yeah, this is what I meant by. So for example, in QFTs, you sometimes have anomalies, and they're perfectly fine. The problem here is that the symmetries that we talk about are gauge symmetries. So these are, this tells you how many degrees of freedom the graviton has, sort of, right? So if you have anomalies, then you also have to have some new constraints to cancel like the new degrees of quantum degrees of freedom that you have. Now, one picture might be that something like what Daniele was saying, like maybe you have some much more quantum degrees of freedom in the UV, and then you recover your classical dynamics through some well-defined appropriate limits. The trouble with this kind of analysis here is that this is sort of bottom-up, right? So now if you include anomalies in your quantum algebra, you don't have a procedure to eliminate these quantum spurious degrees of freedom when you try to go back in a systematic way. Like beta is a continuous parameter. You can go back systematically to your classical algebra. So then I don't know how will one eliminate this kind of spurious degrees of freedom. So I guess the main answer is that anomalies are bad here because they will mess up your degrees of freedom in the gravitational field. And we know that it's 2 in the classical case. So if you allow for anomalies, you also have to tell me a mechanism why this new quantum spurious degrees of freedom will be eliminated in the classical case.
So, but are they going to cause that? Because I'm just wondering, because they're symmetry reduced, whether the gauge symmetries are still sort of local symmetries, or are they?
No. Even so, that's the point. That although these are symmetry reduced, the gauge symmetries that you have, they still have inhomogeneities. They still have anisotropies. So this is just saying that you have one-dimensional inhomogeneity as opposed to GR, where you have three-dimensional inhomogeneity. So the D, for example, in this particular example, has just one component, whereas the spatial diffeomorphism constraint in general has 3 components. So in this case, it is just one, but conceptually it's exactly the same. So the symmetries that you will violate are exactly the same as kind of symmetries.
Okay, thank you. We could conceivably squeeze one more question in, but we do have some closing remarks. So going once, going twice. Then we will say thank you again to our speakers for